Today's talk is going to be on what are the differentiators between the various industrial networks and how do you decide which network to use. So we're going to kind of key in on a lot of the superficial stuff. We're going to try to keep it fairly general and open because there are a lot of industrial networks out there. So we're going to ask the questions and towards the end of this presentation it's like, how do we select between the different and various industrial networks out there? So how we're going to choose that is with these particular topics. So we're going to talk about what are industrial networks and why do we use them. So we're going to do a little bit of history and a little background into that. What are industrial network protocols? So we're going to talk about what is a protocol, because there is some confusion out in the industry on what a protocol actually is. We're going to talk about different network topologies, physical media and infrastructure, so that's the bits and pieces that actually make up an industrial network. Then we're going to look at some common types of industrial protocols, so Modbus RTU, Modbus TCP, DeviceNet, and Ethernet IP, and we'll elaborate a little bit more into that as we go along. We're going to look at some of the criteria for network selection, so that's the whole basis of this presentation, is to talk about the selection criteria. And then at the end, it's a little bit off topic, but we're going to talk about gateways and remote I/O for enabling products to be used on a network. So a little off topic, but really quite relevant in the industrial world. So, what are industrial networks and why do we use them? Primarily, we use industrial networks for process control, monitoring processes, or both. The way control worked was everything was hardwired back to a controller like a PLC. So every little switch or relay or contactor, VFD was all hardwired back to a PLC. So that meant there was a lot of cabling, right? And it's taken some time for the industry to accept networking as a form of control, primarily control, because there was a trust issue back in the day, right? So everybody trusts cables, they know how to troubleshoot it, but now over the years, networks have become more accepted in industry to the point where they're actually mainstay now. And I'm going to talk a bit about why they've become that way. And leading up to that, some of the benefits of industrial networks are a reduced project cycle time. That's one of the reasons. Data acquisition and improved safety. So I'm going to elaborate a little bit about those. Reduced project cycle time. One of the biggest reasons we go with industrial networks is to reduce the overall project cycle time. And what I mean by that is we start from the manufacturer through commissioning and to the point where your plant is actually up and running. So at a manufacturer's level, when we're producing this equipment, you know, as Eaton being a manufacturer, we don't have all these wires going to all the starters and the VFDs. So if you order a network-enabled product from us, we would have the network run into our equipment. So what that means to us as manufacturers is we don't have as much cabling to put in. We don't have all the point-to-point checks, so the commissioning that we do at the plant. So it saves us a lot of time. And by saving us time, it saves the customer time, so we can deliver our equipment faster. Okay? On the customer side, when it gets to site, they would typically do, again, point-to-point checks, because now they've got to connect our equipment out to the valves or the motors or whatever they're connected to for statuses. So now they don't have all those wiring and commissioning checks. So that saves time on the commissioning side of things. Okay, so overall, you got to reduce project cycle time. So from the time the order goes in to the time you have it up and running, we've saved a lot of times by going with an industrial network. Data acquisition. If we think back to that PLC with all the hardwired points going into it, if we wanted to add one more point, we would physically have to wire that point into a PLC. So every time we wire a point into a PLC in the old days, we had to add more PLC cards. So now your project cost just got higher because now you got a PLC rack with lots of cards. As to compare it now, we got a PLC rack with a network card. So we've saved some money there. So data acquisition, instead of wiring your signal to a PLC, now we just ask for it because now these products using network protocols have data available to you at any particular time. So it makes a data acquisition, makes it very flexible to ask for different types of information. Improve safety. With networking, now you can troubleshoot. You don't have to stand in front of the equipment. It's a lot safer now. Okay, you can do a lot of troubleshooting over a network. You could be standing like we have an HMI on that board. You could do a lot of troubleshooting right from there if you tie all the signals back. Signals like your fault log, things like that. You can see what's been going on. So that's kind of a little bit of the background on how we've got to this point with industrial networks. And the three reasons I just explained there, the reduced project cycle time, data acquisition, and improved safety. So now we're going to kind of dig into the kind of an overview of industrial networks and in particular protocols. So what are industrial network protocols? There's a misconception out there that a protocol is the language that gets communicated over the wires. It's a little misconception. It is true, yes, language is a part of it, but a protocol is actually encompasses all the bits and pieces to a network. So as it says here, we encompass all the aspects. We have topology, and we're going to elaborate a little bit more on that. And topology is how we build our network, how we put the bits and pieces together. We're going to talk about the media, and so what we're talking there is the cabling. And then the language, and that's what most people typically associate with a protocol as the language. But a protocol encompasses everything, and we're going to discuss more of that. A protocol also can be thought of as a set of rules, because to every protocol there is an implementation guide, and that dictates your media, your topology that you can use, and the language and how we structure messages. And we're going to break that down individually here shortly. So let's look at the topologies. As I said, a topology is how we hook all our devices together on a network. So if you were to take a piece of paper, and if you envision those little green dots as a device that needed to talk on a network, if you took a blank piece of paper and drew it out, I want this connected to this, connected to this, that's a topology. And different networks can associate with different types of topologies. So the first one we have here is a linear. So as you see here, we go from device to device to device. Some people call that daisy chaining. Okay. Very straightforward. Typical networks that would use that are almost any serial network. This is the simplest form right here. So almost any serial network, and serial I mean using copper wires. Okay. Can use a line topology. Modbus, DeviceNet, almost any of them. Then we have a bus topology. And the difference between this one is they are still all connected together, but that middle line, the thicker black line down the middle between the nodes, that's called the bus. And every little node that comes off of it is referred to as a drop. Some people call it trunk line, drop line, the middle being the trunk line and the little ones being the drop lines. The beauty of this now is that if you have a network on this topology, now you can add devices. Whereas on the linear one, you had to, if you wanted to add a device in the middle, you had to break the network, add the device in the middle. The beauty of this now is we've got a trunk line or a bus structure where if we needed an extra node, we can just, you know, the bus typically wouldn't be that short, it would be long. We would just add another device right on the network. So that's a bus structure. Then we have a tree topology. Little more elaborate. We don't typically have the bus structure anymore. So it's structured like a tree. You've got the trunk typically. So one of these would be a primary path, if you want to call it that way. Then you would have a branch, and off a branch you might have another branch, and so on. Doing this type of topology has very stringent wiring rules. We'll talk about why cabling has issues and stuff. So very stringent rules, but there are industrial protocols that can be developed this way with this topology. DeviceNet is one of these that you could do that as an example. Then we have a star topology. Okay, so looks like a snow leaf. So all the data goes back to one spot. That's a star. You'll typically see this type of topology in an Ethernet-based protocol. Then we have a ring structure. And A ring structure typically is designed for redundancy. And what I mean by redundancy is, you notice how it's in a complete ring. So you have a path. If one of these lines was broken, one segment was broke between two nodes, you still have a path to all the different nodes. So you will typically see this if you're familiar with the IT networking, so data networks and stuff like that at your office. Ethernet uses or is capable of a ring topology. This is not new though. It's not new. PLC manufacturers have been doing this for many years, but it typically has been proprietary protocol to that manufacturer, and we'll talk about proprietary in a little bit. So ring topology is growing, and it's for redundancy, and obviously if you got mission critical equipment, you don't want downtime, so any redundancy is good. So that's the topologies. That's not all the topologies out there, but that's the ones you would typically see in an industrial network. Then that leads up to, how do we build this topology? And that's where the network physical media and infrastructure comes in. So how do we connect things? We use cables, right? In most cases, we use copper cables, okay? Couple points about copper cables. Low capacitance. A network is a form of communication where it typically uses digital communications. So we have a binary string. So how we communicate is with voltage levels, by putting a square wave of voltage levels. We have ones and zeros. A 1 being a high voltage and a 0 being a low voltage. Now we send that out at different frequencies depending on the protocol. What happens is if you have a lot of capacitance in a cable and you send a square wave, like you want to send a 1, so you're going to send a square wave down the line. With a lot of capacitance, it charges the cable. And when you get cable charging, you can get ringing on your line. So where you wanted a nice perfect square wave to be a 1, now you've got ringing going on because you're charging the cable and it discharges and charges. So now you got ringing on there. Plus, if you have a long network, that ringing can actually get reflected back. And what happens is, if you have a lot of capacitance on the cable, it really limits the length of your network. And if it's too high, you can actually get communication errors. Because is that really a 1 or is that a 0? We're not sure. It's ringing. It's no longer a square wave. You kind of got some other stuff on top of that. So typically, a protocol will specify what cable to use, and it typically will be a low capacitance cable. Then we come to shielding. The picture at the top is looks like a 4-pair, so an 8-wire without a shield. And the bottom one there is the picture of one with a shield. So it's got a foil shield and a drain wire. All industrial networks should use a shielded cable. And what shields there is for noise immunity. Okay? If we have noise on our data lines, remember I said we have voltage signals, right? A 1 being somewhere in the realm of 3 to 5 volts. If we start getting noise on there, you can induce more voltage onto a cable. So then how does that network interpret that? Noise can cause errors, which bogs down a network to the point where it may even lock up devices on communication. So we want to use shielded cables. We talked a bit about the network length. A cable, it has resistance, it has capacitance. Okay, we can only go so long, right? What happens with the resistance, that little 5 volts we were sending out, it gets obviously reduced by the time we get down, right? So we have a fixed length that we have to adhere to. Termination. A cable has a characteristic impedance. And if we want to eliminate that reflection thing, we have to terminate at both ends. So we put impedance matching terminators on. So serial cable can be anywhere, 100 ohms, 150 ohms. But the characteristics of that particular cable, we would put terminators on both ends to get away from reflections. Then we come to number of conductors. There's some serial protocols, RS-232 I didn't put up there, RS-422, RS-485. That dictates how many conductors you actually need. Ethernet. Okay, are you using all the pairs, some of the pairs? Okay, there is a specification for Ethernet. And then we get it down into half duplex and full duplex. That ties into how many cables you have. In a half duplex system, you typically cannot transmit and receive at the same time. Okay, you can transmit, but then you got to wait because you got to receive something. Full duplex means you have two sets of data lines. You've got a transmit line and a receive line, so you can do both at the same time. So obviously a full duplex system is going to operate at a lot faster communication speeds. Then we have fiber optic cables. Okay, they're still a cable, they're just not copper anymore. Now they use light. The reason people would go to a fiber optic cable is to extend network lengths, because now we no longer have that resistance in the cable, do we? We're just using light. Light can travel a lot farther than a voltage signal on a cable that has resistance. So we can extend our network length. The other reason we would go with fiber optic is noise immunity. Now, you know, previously when I talked about the shielded and unshielded, noise could get induced into a cable in the form of a voltage signal. We're using light. As long as light doesn't get in, we're noise immune now. Okay? But there's some drawbacks to that, is typically you require industry standard connectors, and repairing fiber optics can be a specialized field. So you get some advantages, you extend your network length, you get noise immunity, but it may be a little bit harder to implement. Then some more on the physical media infrastructure are components. A protocol in the implementation guides may dictate what type of connectors to use, what type of T's to use, what type of terminators, bus extenders, all the pieces associated with developing a network. So if you look at some of these, this is a snapshot of a DeviceNet product. So DeviceNet specifies the type of cable to use and the type of components to use. As the example, if you're using a T, that's because we need to build a topology. Well, without T's, we can't do a bus structure or a trunk line, drop line structure, and so on. So that's still part of the protocol, is the infrastructure. So we talked about topology and the media. Now we're going to talk about different network design and types. So now we're kind of getting more towards the language part of things. So how do we communicate over this network? So some of the terms you may see are a master-slave network. And what a master-slave network is we have one master, and it's the only one allowed to talk to the slaves. Okay, so a master would send out a response, the slave, or a request, and the slaves would send back a response. There are some protocols that allow multiple masters. So you could have more than one device talking to the slave devices. You would typically see that like in an Ethernet network, where you might have, as an example on this board here, we could have that screen talking to a device. We could also have a PLC talking to a device. They're both masters. They're both requesting information. That's a multiple master network. Then digging deeper into protocols, there are different types. There are something we call open protocols. These are the languages that are publicly available, and they are open to everybody, and it's developed by a committee of companies. And typically there's a board of governors, and all these members and governors, they get together and say, okay, these are the features we want in our network. We need this, this, and this. And they talk about it, and they come up with a strategy and so on. That's an open protocol. There are proprietary protocols. What that means is that protocol is owned by one company. Okay? It may be openly and publicly available, but you have to abide by their rules, and you typically don't have input into the features that are in there. Okay, so it's a little more locked down. You don't have as much flexibility. Okay, so here's an example of some of the governing bodies. As an example, Modbus. If you go to their website, modbus.org, it has all the documentation you need to implement, and you can also join as a member. And it also lists all their members. Okay, DeviceNet and Ethernet IP, they're governed by ODVA, Open Device Vendor Association organization, and I put one in there on the bottom, Profibus. Now, Profibus is somewhat of an open/proprietary protocol. There's different flavors of Profibus. Okay, now protocol conformance and certification. With protocols that have governing bodies, typically they will have a certification and conformance testing procedure. You ever see a device that says tested or something like that, or tested or conformance tested? They go through benchmark testing. So when they give you this protocol, and as a manufacturer we develop a product, how do we know that we're actually going to work properly? Well, we send it to these conformance testing places, and they will test it to a benchmark. It has to meet minimum requirements. And after it has done that, we get a certificate saying, yes, you are compliant on this network. Okay. The reason for that is, one, that it meets, pardon me, I put all on my presentation, but it meets the design criteria that you've implemented into your product. Okay? So the reason for that is you reduce the risk of product compatibility problems. Okay? I've heard lots of stories where you got device A and device B, they're supposed to talk to the same protocol, but guess what? They kind of do and they kind of don't. This is supposed to reduce that risk of interoperability problems. But my bottom note, some protocol implementations only use portions of a specification. There are protocols that insist on implementing certain features, but they also have many optional features, and it's up to the manufacturer if they want to actually implement that into their product. So when they do these testings, they will test the features that you actually implemented. So that's where you get into the interoperability problems, right? You may have a device here with the necessary options or the necessary requirements, and you have this device that has some optional, and they don't really quite talk the way you would expect. So it's not a perfect situation, but conformance testing does guarantee that the necessary development tools have been implemented. So now we're going to talk about some more of the common industrial network protocols, just to give you an idea of, try to lead you in the path of how do we select which one to use. So Modbus RTU protocol. It is a serial communication protocol. It uses the RS-232 and RS-485 serial line implementation standard. That's the physical part. Just to talk about RS-485, we see a lot of specifications that come through our office, and the specifications will say, must have RS-485 communication. And I go, okay, what's the protocol? That's just a portion. The 485 just means it's the wiring standard that we apply to. They want a 485 network, but without telling us what protocol they want, we're kind of out in the dark, right? So then I go back and say, we need to find out what protocol they want to make sure we can support it. So there's a little misconception that way as well. So as far as specifications go, we need to know the protocol, because the protocol, like I say, encompasses everything. It tells us what you need. Data rates. In today's terms, it's a relatively slower data network, 9.6 kilobit per second, all the way up to 115 kilobit per second. And it is a master-slave communication device, so you can only have one master, multiple slaves. It uses acyclic messages. What acyclic means is unscheduled messages. When we're talking messaging, we can have unscheduled or scheduled. Unscheduled means I'm a master, I make a request, I get a response. And then I can do some other things. And then if I need information, I'll make another request. I'll get another response. Cyclic messages are scheduled. And what that means is you ask for that same data all the time in a scheduled manner. They call that cyclic is deterministic, acyclic is non-deterministic. So the Modbus RTU protocol is an acyclic message protocol. You can develop some sort of deterministic through your messaging structure, but it is not developed around a cyclic-based structure. We can do broadcast messages. That means we can send out a message that goes to everybody, all the slaves. Because typically you would go, I'm a master, I'm going to send a request, I want this information from you, and I want that back. But you can also do a broadcast that says, everybody do this. That's a broadcast message. You can have up to 247 slave nodes, and a little sub-note, 32 devices without a repeater. A repeater is a way to boost it boosts your communication signal. So it extends your network length. Then we have Modbus TCP protocol. And it's basically using the Ethernet form of communication, which again is a physical media to some extent. It's also got some other software features as well, but it uses the TCP Ethernet frame to transfer Modbus RTU signals. So it's like Modbus over Ethernet, Modbus RTU over Ethernet. But what it does allow, it allows for more flexible topology. Now we can do our ring structure where we couldn't do that with the Modbus RTU. Okay, so the other thing is you can have multiple masters. Now you can have more controlling devices. You can have a lot more many nodes, depending on the Ethernet class that you have. You know, I know it's getting out there, but class A, B, C, and D, you can have a small number of nodes, you can have lots of nodes. So you've got a bit more flexibility, you're not stuck with your 247 nodes. It allows for multiple protocols. Now that we're on Ethernet, we can not only do Modbus TCP, some devices may have a built-in web server for diagnostics. That runs on a different protocol, typically HTTP. So we can run multiple protocols through the Ethernet network. Okay, again, more flexibility. Now, the way Modbus TCP works is it's a client-server acyclic messaging system. A client-server is another way to say master-slave. A client is the one that requests information, and a server responds to information. Then we get to DeviceNet protocol, which is very common. More of a North American industrial network. It is governed by ODVA, and that little symbol at the top, the DeviceNet with the checkbox, that is the conformance-tested logo that they use. It uses a CAN network, controller area network, that was developed out of Europe. All our vehicles typically run on CAN, but it uses a portion of the CAN protocol. It uses the bus structure, so now we can allow for the active addition of a device onto the network. 64 devices per network, and we've got data rates of 125 to 500 kilobits per second, so faster than Modbus RTU. One of the other criteria of this particular protocol is that the power and communications are run over the same cable, not the same conductors. What they're saying is, in a cable, you've got power and you've got data. So you have five conductors in that particular cable. It uses what we call SIP, which is a common industrial protocol. So there is some different levels to networking. You've got your physical level at the bottom, which is your cabling, and then you've got your network level, and all the way up to your application level, which is your protocol. So the common industrial protocol is a list of what that is structured as. It's a little more advanced, so now we got network monitoring. So we've got connection-based information going back and forth. It says, okay, is that node there? Is this node there? There's stuff going on in the background that we don't see. That typically doesn't happen with like a Modbus RTU. So it's a little more advanced as far as connection goes. Then the last one here is Ethernet IP. And it can be thought of as DeviceNet messages transferred over Ethernet. You know, we had Modbus and Modbus TCP. Now we got DeviceNet, we got Ethernet IP. That's kind of the quick and easy way to explain it. It's not entirely 100% that way. But it also uses the Common Industrial Protocol. It has deterministic data, as well as DeviceNet did. Sorry, I didn't put it on the last slide. So it does use scheduled messaging. It has cyclic data transfer. Again, it has network monitoring. It uses the Ethernet media, so now we can expand our network through routers and switches. We can have multiple levels. And it, again, is governed by ODVA, and there is a conformance-tested logo there on the bottom. So, as a quick overview of those 4 networks that we showed, when we're selecting a network, it's good to have a little chart like this to kind of see, okay, what's different between the 4 of these. So I put this little chart together. So the things that we've talked about so far is topology, the media, we looked at some data rates, distance with no repeaters, even though I said 32 nodes, but we'll get to that a little bit later. Well, actually towards the bottom here. Number of nodes you can have on a network, that's another question to ask. And what type of communication? Do we need deterministic information? Do we need cyclic? Or are we okay with just asking for information, and when it gets back to us, we're okay with that? But as a note here, you see under device net here, it has 5 different types of connections or way to get information out of a device net. We've got explicit messaging, which is acyclic. We've got polled information, which is the most common way people connect device net. It's a deterministic cyclic information. We got bit strobe, change of state, and it is a master-slave network. Now, when we had talked about Ethernet, saying we could have multiple protocols on one Ethernet network. You have to be aware that in an Ethernet IP system over here, even though it's Ethernet, we can have multiple protocols. You can still only have one master with Ethernet IP operating Ethernet IP slaves only. You can't talk to Modbus slaves, so you still have to talk the same language. Okay, so, and all this stuff is outlined in the implementation guides of every protocol. Okay, so how do we select which network? Okay, realistically, it's what's important to you. So you're gonna have to sit down and you have to decide, are we doing control? If you're doing control, you may want to look at the deterministic data, so cyclic data, things that are scheduled all the time. If you're just doing monitoring, maybe not so much. It's not as critical because the control is being done somewhere else. Or if you're doing both. Another point to ask yourself is industry acceptance. Different industries accept different protocols. Industrial have a set of protocols in North America that might be different than industrial protocols over in Europe or Asia, right? Utilities have their preferred protocols. Building or commercial industries, like in building HVAC systems, they have their set of preferred protocols. So it really depends what industry you're putting the network into. Is your protocol that you selected supported by multiple vendors? Are you fixed to just having that one vendor's product, or can you use anybody's product? Okay, it allows for more flexibility. We talked about the topology. Do you need redundancy? Do you have to expand in the future? And if we have to expand, can we add nodes on the fly, or do we have to shut everything down to do it? Is it easy to implement? That means a lot too. A Modbus is a very simple protocol to implement, whereas a device net or Ethernet IP probably takes a little bit more. Is there any special hardware required? Like I said, a protocol dictates the media you use. Is this hardware readily available from a distributor or from a manufacturer? Reliability, network uptime. If we're doing control and our network goes down, our process went down. How mission critical is it, right? So network uptime, how robust is the network? Response times, we talked about the deterministic and the scheduling of messages. Network security, now that Ethernet is becoming more and more prevalent in industrial, how secure is that? Are we going to hook our Ethernet, our industrial network, onto our IT network so the accountant in the corner can actually access our PLC and start monkeying with our process? So there's some security questions you got to ask yourself. Do you need multiple masters, multiple protocols, product conformance certification, environmental conditions, operating temperature, noise immunity? Is our environment relatively noisy? We may want to go to fiber optics. Serviceability. Is there any special hardware required that you would have to purchase? Is support, is it available? Is it available just from the manufacturer, or is there outside industry resources that we can pull on? for troubleshooting. Network and protocol familiarity. You may have an E&I group at your plant. How familiar are they? Is it brand new to them, or have you been using that for some time now? You may have to look at your technical capabilities in your company, deciding which network to go with. And as well as troubleshooting tools, hardware tools. Are there any media checkers? So a network goes down, now what? I don't know, start changing cables, or maybe put on a device that tells you might have a break in a wire somewhere. Okay, software tools, protocol analyzers, a way of configuring devices over a network, a way of testing devices over a network, that kind of software tools, are they readily available? Okay, so those are a lot of the questions. It's not all the questions, it's the ones that I find are very common for selecting a network. So that was kind of the presentation on the industrial network portion, but now I want to take a little bit of time and talk about protocol gateways, because you will find them on a network. And what a protocol gateway is, it's a device used for bridging products with two different network protocols. Okay, so we have our Modbus and we want to talk device net. How do we do that? We do that with a product called a gateway. So it enables us to talk to each other in both directions. So there'd be a box here, Modbus this way, device net this way, and somehow messages go back and forth. So it does all the translation. So it addresses any topology, physical media, or protocol compatibility issues. That's what a gateway does. There are some specifications out there that say they don't want gateways, but the actual truth is you find gateways almost anywhere. If you look at a PLC with a network scanner module, and let's say it's Ethernet IP, is that actually the language that PLC is talking? No, it's not. It's a gateway to put the information on the bus of that PLC. So there's gateways everywhere, even though you don't typically see them or know they're there. And a gateway allows for greater flexibility for process design. So say you have this manufacturer that has his product over here, but he doesn't talk our language, and you got another one over here, he don't talk our language. You put gateways in, because that's the process you built, and that's the product you want. Now, we also got products that are non-communicating, but you want them to participate in a network. We use a product called Remote I/O. And a Remote I/O is a communication adapter with I/O on it where you can connect your digital signals, your analog signals, and now we can get that over the network. So we can control the monitor over network. And where you typically see this is on legacy products, older products that were never implemented with communications. But they're still out there and you don't want to change them. You still want to use them. So gateways and Remote I/O allow for a lot of flexibility with older products. And now just to wrap up, I got a slide here on the network trends. Ethernet is a growing market. More and more we see people wanting to go to Ethernet. Now Ethernet's not a protocol, right? Ethernet is a form of connecting. It's a topology in a physical media scheme. There are a lot of Ethernet protocols out there. Probably tens, maybe hundreds. Okay? They do that to get the benefits from the IT structure. So now we can design our topology. We can use the Ethernet switches, Ethernet routers, and so on. Typically not the ones you buy from the electronics store. You want a hardened industrial type of infrastructure. We can web-enable products with Ethernet because we can do multiple protocols. Remote monitoring. Now you can view what's going on with your process. You don't have to be at the plant. You can be at home or wherever. Talked about multiple protocols. We talked about remote monitoring. Typically, you would link that through the internet in some form or another. Wireless. I never got into wireless, but that's a whole separate topic altogether. That offers a whole wealth of possibilities with topology and flexibility. But the topic today was more so on the questions on what to ask. So I kind of left the wireless more of a bullet for consideration in maybe possibly another presentation.